Okay, so today we are going to start introductions on various reactors that we will discuss. So, in our previous class we already have studied about various industrial reactions. So, what are the reactions commonly used in industrial scales to get a particular product. So, that we have discussed. So, almost all reactions in chemical engineering point of view, whatever we will study mostly will express in terms of A plus B going to C plus D. So, that you can see here. So, A plus B, that is the reactant that is going to product when it is in a reaction. So, that giving the product C or and D. Okay. So, depending upon the reactions that will vary. So, now once we have decided to means we have selected a particular reactions to conduct that reaction to get a particular product, then we need the reactors. So, the reactor is the very important thing. So, we have to choose a particular or proper or reactor. So, then we can conduct that particular reactions properly. Okay. So, there are so many reactors. So, out of them first one is the batch reactor, you can see here. So, that is the very common batch reactor. So, there we can take that reactors, very simple reactors, there we can put reactant A and B from the beginnings, the known quantity, and then reactions will be carried out over there. And after a certain period of times, that may be 10 minutes, 20 minutes, 30 minutes, we can stop the reactions and then we can analyze the product. So, that is the batch reactor. So, there is no in or outflow of that reactors, that is the very simplest. Next one is the CSTR reactor. So, you can see here. So, in this particular reactors there is inlet of the reactants that is coming here, and after that reactant enter inside of the reactors, reactions will start and then product formations will there if we maintain that particular desired temperature and pressure. So, then the product will forms and then that product reaction mixture that will come out from the outlet of the reactors in a particular molar flow rate or in particular concentration. So, in this type of reactor there is a stirrer is there also, you can see that one stirrer is there. So, when the reactions will take place continuously stirring would be there. So, therefore, this type of reactor is called continuous stir tank reactor. So, next one is the plug flow reactor, this is also similar like that of reactor. So, in this type of reactors one tube is there, through that reactant will be fed from the left hand sides and reactions will be take place at a particular temperature and pressure. Then product formation should be there, that product will come out from the outlet of the reactor. So, here when the reactions will take place inside of that type of this type of reactor. So, the concentrations of or molar concentration of that particular reactant gradually decrease or along the length of the reactor, this is the along the length. So, this is the you can say length of the reactor. So, if we go from left hand side to the right hand side, the concentrations and rate both will change from point to points. Okay. So, this type of another reactor, and there is another reactor that is the packed bed reactors. So, here similar to the plug flow reactors. So, here only difference is that here inside of that reactors catalyst particles would be there, that will be placed inside of the reactor and then at a particular temperature and pressures we can maintain and that particular temperature and pressure, and reactant will pass through that bed, then reactant will be converted into the particular desired product. Okay. So, that desired product or product outlet streams will get that particular product on and reactant mixture that will come out, that we can get and analyze to get the percent conversion, yield, selectivity for that particular system. Okay. Similarly, semi batch reactor is also, this is similar like that of batch reactor, but here so one if there are two reactants are there. So, one reactants will be placed from the beginnings of inside of the reactors and then A will be flow or enter inside of the reactor to for that particular reactions, but we can control the flow or addition of component A inside of the reactors for that particular reactions. That way, if you consider A plus B both are the reactant for the reactions, when both will be present inside of the reactor, then reactions will take place. So, from the beginning large quantity of B you have taken, but A was absent. So, then when limited quantity A will come, then reactions will start. If you do not feed any A, then reactions will stop. So, that is the beauty of this particular reactor. So, there are other type of reactors, that is the recycle reactors also. that is similar like that of plug flow reactors, but here recycle stream is there. So, this is the recycle stream. So, what are the product mixtures will come out. So, that one part would be sent back to the feed stream. Okay. Then that way we can continuously maintain isothermal temperature inside of the reactors, or if you want to increase or decrease of the temperature of that particular reactor, that we can control. Okay. This is the means added advantage in compared to the plug flow reactors. Here continuously stirring or mixing also may be possibilities there. Okay. So, next there is another kind of reactor, that is the fluidized bed reactor. So, here you can see this is the fluidized bed reactor. So, in this type of reactor mostly used for cracking reactions. So, suppose in we have a naphtha, that is crude or naphtha. If you want to crack that into smaller component, that is naphtha to gasoline production. So, then this type of reaction, there is a means deactivation of the catalyst possibility is there. So, in that case when regular catalyst changes are required or regeneration of the catalyst is required. So, then we can pass the catalyst and reactant gas from the bottom of the reactor. So, here it will be passed and it will be enters, and here it would be means fluidized bed means here the catalyst particle will be very small. So, with the flow of the reactant feed rate would be such that reactant catalyst particle may be floating there. So, that will be passed with that reactant mixtures, and then reactions will be take place there if we maintain a particular temperature, desired temperature there. So, once reactions will be over, then that catalyst and product mixtures will come to the disengagement sections there. So, we can separate out the catalyst or deactivated catalyst or spent catalyst, and product mixtures will go out from the reactor. So, that way also fluidized bed reactor that does operate, or that way we can consider this type of reactor. So, apart from that there is some trickle bed reactor is also there. So, in trickle bed reactors you can see here 3 phase reactors. So, in this particular type of reactors, here you can see one gas, another liquid, and here the solid is there, solid catalyst, that may solid catalyst is there, that catalyst bed from the beginning it was there, and when gas and liquid that as a reactant will enter from the top of the reactor, it will pass through that catalyst, and then at a particular temperatures or pressures if we maintain inside of the reactor, then it will be converted into that desired product, and that will come out from the bottom of the reactor. So, here 3 gas, liquid, solid, 3 phases are present, and that way that reactors we can use for a, mostly it is used for hydrodesulfurations of heavy oil stocks. So, in that case it is used for that. So, other purpose also we can use this type of reactors. Apart from that, there are slurry type of reactors. You can see this is also similar like a trickle bed reactor, but here catalyst was present inside. This is the solid catalyst, here this is the solid catalyst is present inside of that reactor, and here liquid is also there from the beginning, solid and liquids, and we maintain particular temperature for that reactions, and from the bottoms we can pass that gas, second reactant gas, that is we can pass through that reactor from the bottoms, and that will, when it is passed through that bed, then catalysts, liquids and gas is present, that will be take part in the reactions at this particular zone, and then reactions will take place, and after a certain means depending upon that longer means residence times or contact times required, based on that reactions means reactant will be converted into the desired product. So, that way that type of reactions or any reactions having this type of catalyst, liquid and solid is required phases, 3 different phases. So, in that case we can use that. So, these type of reactors mostly used for hydrogenation reactions. Let us say we have a long chain hydrocarbons, there is unsaturation or unsaturated bond is there, we want to saturate them or hydrogenated them. So, then this type of reactors we can consider liquid as a one reactants remain there, and from the bottoms we can placed means pass that hydrogen gas, and then that would be react that or converted that reactant into corresponding that product. Okay. So, this type of reactors we can use. So, another type is reactor is the moving bed reactors. Okay. So, this is also a moving bed reactor, state through transport reactor. These are the type of typical reactors mostly used for the places where cracking reactions is there in the petroleum industry, where petroleum heavier fractions usually cracked to form gasolines or lighter components from heavier compound to lower molecular weight compound. In that case catalysts are used in that particular cracking reaction. So, it has been observed that when that reactions will take place, so then carbon or coke formation is there, lot of coke formation is there, that would be deposited over the surface of the catalyst, then catalyst will be deactivated very fast. So, depending upon that reactions catalyst will be deactivated very fast. So, then we have to stop the reactions, but it is not possible for continuous process to maintain the continuous operation. So, here in the moving bed reactor you can see this part is the reactor. So, where reactions will take place, catalyst will be placed reactors, their catalyst and reactant most here fit through that reactant will enters, and here from this path catalyst will be charged with the feed into the reactor, reaction take place and inside of the reactors, and then product will be come out from that lines and the spent catalyst or after reactions. So, that catalyst will be come down take out from that reactor to this kiln. So, there's we can means regenerate that catalyst once the catalyst is deactivated, that will be take out send theirs, and then by charging airs or gasification of that particular coke we can remove that coke materials and from that surface of the catalyst, and then we can regenerate that catalyst. After that it would be sent back to the here for again in the separator. So, there again as a with the fresh catalyst will be charged into the reactor for continuously maintain or continuous production. We can use or consider this type of reactors. Okay. So, here right hand side you can see this is the means catalyst movements, means in the moving bed reactor this is catalyst beds you can consider. So, that catalyst bed having a particular movement or velocity, mass velocity particular kg per second at that would be moved down in that particular reactors from top to bottom, and that would spend particular time within that particular reactor, and when the reactions will take place, by that way the cyclic process would be there in that particular type of reactors. So, this is very useful reactors. Similarly, straight through transport reactors, this is also another type of reactors. Here are also for the purpose is the same, means when the catalyst deactivate very fast. So, for that purpose also we can use this straight through transport reactors. Here also fresh catalyst will be charged from the bottom with the feed gas well, and that will be passed through a tube. It tube is there, here you can see through that tubes reactants and catalyst both come in contact and will maintain that particular temperature, then that will be react on that particular tubes, and both reactants and gas product gases will be come out, and here disengaged stripper is there, here that would be separated out, and catalyst would be come down from the bottom that will be sent back to the regeneration units. There's that spent catalyst would be again regenerated into, means active sites will be regenerated, and coke will be means oxidized in presence of air or any other oxidant. So, that will be removed from that surface of the catalyst, again that catalyst will act as a active phase regain its activity, and then again that will be by that we can maintain a particular process continuously. Okay. So, next is the membrane type of reactors. This is also another type of reactors. Here feed would be here that will be means pass particular tube is there, through that there is a membrane is there. This is the membrane, and through this membrane there is some pores are there in the membranes. You have you know that in membrane there is some pore or porosity is there. We should place the catalyst here inside of that reactors, and when reactions will take place, and the reactions may be let us say cyclics into benzene and hydrogen formation is there. So, that hydrogens will be come out from that particular membranes. In the membranes there is the pores, through that it will be come out, and we can separate out during reactions, and the other heavier component that would not pass through that membrane pores, that will be come out as a product from here, and we can get a second product, means that another side. So, by that way we can increase the conversion selectivity of that particular reactions or products. So, that way we can means separate out also, means these reactions may conduct at high temperature, can separate out that a particular product when reactions will take place. Means that catalyst, if it is required, we can place as a bed inside of that reactors this type, or maybe with the membranes, when we will prepare the membranes, with that also catalyst will be placed. So, over the surface of the membranes, catalyst in the form of particles would be there, and with that when reactants will pass through that catalyst or reactors. So, reactions will take place in presence of catalyst, and similar phenomena also, or similar type of means catalytic operations and separations also we can conduct this using this type of membrane reactors. Similar type of other aerosol type of reactors is there. This type of reactors also used for productions of nano size metal particles formations or particle formations, that is also used. And micro reactor is also there. There is micro channel reactor or micro reactors you can say. So, here this type of reactors means the catalyst or the channels through which the reactant will pass, the dimension is very small, therefore, it may be less than 1 mm or width and length would be within that range, very small range. So, therefore, this type of reactors is used or considered as a micro reactor depending upon that dimension of the reactor. So, mostly the any type of reactors objective is to place some catalyst, conduct some reaction, will get some product. So, that is the objective, but here dimension is very small. So, therefore, it is micro channel or micro reactor is called. This type of reactor commonly used for as a chemical sensor, chemical screening, synthesis of specialty chemicals, these are commonly used. So, apart from that there is other type of reactor, that is CVD or chemical vapor deposition reactors also you can say. So, these are the reactors are very useful for fabrications of microelectronic devices, carbon nanotubes, we can easily prepare using this type of reactors. So, here in this type of reactors, so this is the red color you can see, this is the furnace, temperature would be maintained, and here is a tube is there, inside of the tube so we can place the catalyst over there, and reactants that may be methane, ethane, propanes or cyclohexane, ethanols, any kind of reactants that we need to deposit over the surface of the catalyst, that we can pass with the carrier gas, that would be passed, and in presence of catalyst reactions will take place, and then the deposited coke or carbon nanotubes, multi wall, single wall, double wall. So, that may be any one that would be deposited over the surface of the catalyst or formations inside of that reactor, and after that the others gases that will come out. So, by that way we can prepare nanomaterials also using this type of reactors. So, apart from that there are bioreactors also there. These type of reactors commonly are used for enzymatic reactions, means growth of microorganism, for the production of antibiotics, insulin and various compounds, bio related reactions if you want to conduct. So, then this type of reactors we need to use to carry out the reaction. So, here is one, if you see in this type of reactors, cooling circulations outside of the reactors, cooling jacket is there. So, there is water would be supply, one inlet line is there, outlet is there. By that way we can maintain an isothermal temperature for the reactor to maintain a temperature constant or fixed temperature based on that particular reactions we need, that may be 35 degree centigrade throughout 24 hours we need. So, by that we can maintain. So, here we can supply air also, inlet is there. So, that would be from the bottoms it would be make bubbles inside, if it is inside there is some liquid is there, through that we can purge that bubbles, or we can supply the air or oxygens to carry out the reaction if it is aerobic reaction. So, and continuous agitator or stirrer is there, magnetic stirrer or that stirrer is there, agitator is there. So, stirring operations also would be there. So, this is bioreactors. And apart from that there is high pressure reactor that I already have discussed. So, about batch reactor, this is one kind of batch reactor. Here volume is fixed, but pressure would be different, volume constant, pressure would be changeable, means if we need for a particular reaction, let us say 10 bar, 20 bar or 50 bars. So, reaction temperature let us maybe 500, 600, 300 degree centigrade we want to conduct reactions, we want to change the pressure. So, then for that particular purpose we can use this type of reactors also to maintain a high pressure for that particular reactions. Now we have discussed different type of reactors commonly used or available for industrial operations or lab scale study also we can use this type of reactors. Now we are going to discuss about the design equation or a particular reactions. Okay. Reactors, we know the reactions, we know the reactors, different type of reactors. Now we have to do the or develop some design equations once we have to use a particular reactor or once we choose a particular reactor for a particular purpose, then we have to know that particular reactors and its design equation. The design equation is very important to design a reactor. So, therefore, let us say means at the beginnings we will develop a general mole balance equations and then by choosing a particular reactors we develop the design equation for that particular reactors. Okay. So, that may be batch reactors, plug flow reactors, continuous start tank reactor or packed bed reactors or maybe other reactors, the design equations depending upon that particular choice of reactor. So, we can implement that particular design equations to find out the volume of the reactors or catalyst size means catalyst quantity is required that we can develop. Okay. So, or we can compare volume of one reactor to the another reactors. Okay. So, here to start that general mole balance for that system. So, let us say this is a system, this volume system volume is known, that is the V volume for this particular system. So, here this is the f j 0 for a element that may be j component that is the reactant or maybe component A that is the reactants either A or J whatever. So, in terms of anyway we can express the reactant molecules that is feeding in within this particular volume that would be entered for that particular reactions once, and G j that is the rate of generations of that particular component J, that J may be component A, component B or any kind of reactant that we are using. Okay. And this is the F j that is the molar flow rate. Okay. So, F is the molar flow rate, mole per unit time. Okay. Molar feed rate, and if it is batch reactor then only moles would be there, so there is no flow. So, that we will discuss later. So, this is in terms of this is inlet, this is outlet, and inside of this particular volume or specified volume or space within that or system volumes that reactions will take place, means rate of generation of that particular component or disappearance of that component, the things will be there. So, next if we conduct the mole balance of a particular system, so then these are the component will come rate of flow of J particular components into the system, and then coming to the rate of generations means of that particular species by chemical reaction when the or when that particular component is inside of that system or reactors, that is equals to rate of flow of out from that systems of that J component unreacted component that is leaving from the reactor, and then accumulations or rate of accumulation within the systems of that particular J, means maybe some component depending upon that reactor may be ideal, the reactors we have designed not ideal, non ideal or real reactors. So, then maybe some compound may be accumulated inside of the reactors. So, then that also we have to count for the mole balance. So, then if we simplify this equation, input plus generations minus output equals to accumulations, or we can say input plus generation that is equal to output plus accumulations, or we can write or we can express this in terms of F j 0, that is the input of component J at time t equal to 0, and this is the generation part G j, this is output or outlet from the exit stream that component J would leave from that reactors, and d n j by dt that is the accumulations of that component within a stipulated time. And here's rate of generations we can express G j that is equals to rate of generation, and within that specified volume that we have to multiply it, then that would come mole per unit times. Okay. And N j is the number of moles, R j is the rate of formation of the species J. Okay. So, now in the rate of generations in the general mole balance, the formation of the J species for the reaction that will vary a position to positions. Let us say here this is a reactor, batch reactor we have taken, here positions 1, here position 2 we can say. So, in particular small volumes or elements of volumes we are taking here dV 1s and here dV 2 delta V 2, that is the specified small volume that we are considering, and within that reactions will take place individual space or that specified volume or system volume. So, within that particular rate would be there. So, if we consider in that particular point 1 rate it R J 1 and for point 2 their rate it R rate of that particular reaction is R J 2. So, then at for locations once we can write rate of generations R this equals to this, and for specified point is delta G J 2 that is equals to R J 2 into delta V within that volume. So, like that any other place also within that systems we can consider, and by that way we can sum up the total generations, the total rate of the generation within the system volume is the V. So, thence we can write G J that is equals to summation of all individual points and corresponding rate. So, thence that would come this, if we express this in terms of this G J equals to integration volume total volume, if we consider R J is the rate of individual that particular point or locations or specified volume. So, then if we sum up then that would rate of generation part would coming like this. Okay. So, then the mole balance or material balance equation that we can write this, it is coming like this. Okay. So, F j 0 minus F j and generation part and accumulation part is this. So, this way we can writing, this is the general mole balance or basic mole balance equation for any system. So, now this we can use this general mole balance equation for any reactors, other reactors also we can consider, and depending upon that so we can apply that. So, now we will consider this general mole balance equation for a batch reactor. I said that this is a batch reactor, here's inflow and outflow, that is there is no inflow and no outflow, this is outflow and this is inflow, means there is no inlet no outlet. So, only this specified volume is there where component A and B will be placed within system volume is V if the rate of reaction is R J. Then from the general mole balance we can say that here F j 0 that is the here F j 0 and this is F j. So, both are 0 since there is no inlet no outlet. So, then this part is 0, then this is our general mole balance. So, this part we can put 0 and then only rate of generations, and this part will be living in the for this batch reactor. So, then we can write this equation this way. Okay. So, now we can write also for J species के लिए for the species or components J the d n j by dt equals to R j into V. So, or for component A also for that we can write this. This is the design equation for the batch reactor minus d n a by dt equals to minus R A rate of the reactions and total system volume. So, this way we can express the design equations. So, the batch reactors there are two types, that may be constant batch reactors that you already have studied in your UG course. Again I am repeating this, means this is the constant volume batch reactor, this is variable volume batch reactor. So, either way we can use, and here volume is constant, here pressure is constant, here volume is variable. So, here is variable volume batch reactor, here this is the constant volume batch reactor. So, if we start from this design equation, so here if we constant we said V is the constant, then we can put it here and then we can express d n a by dV by dt equals to minus R A, that is equals to minus d C A by dt equals to minus R A, that is the rate equals to we can express R A equals to for R A, that is the for component A d C A by dt, that way we can express, means rate we can express in terms of concentration also. This is also design equation for a constant volume batch reactor, and similarly for variable volume batch reactors here V is not constant. So, then we have to express this way, means differentiate, and then this is the final equations we can get. This is d C A by dt plus C A by V dt dV by dt equals to R A. So, this is the design equation for variable volume batch reactors. Okay. So, now we have discussed means what is the design equation for a batch reactor and minus d n a by dt equals to minus R A into V, that we have studied. So, similarly we have to use the general mole balance equation for other type of reactors, and we develop the design equation for that particular reactors for further study to evaluate or design the particular volume is required for that particular reactor. So, when we conduct any reactions and we will choose that particular reactor. Therefore, that is important. So, these are the things we will discuss later in our next class. These are the things notation I think already you have studied. Again you should means remember it that Na that is the expressed in terms of moles and V that is the volume that expressed in terms of dmq, meter cube or liters of the system volume, and this is the molar flow rate, mole per unit times. So, here we are expressing that is equals to Fa, that is expressing in terms of molar flow rate, that is multiplied with Ca into small v is the or volumetric flow rate dmq per second or minute unit times. So, here we have express it, this is the same thing. So, dmq per unit time volumetric flow rate, here is the concentrations d Ca mole per dmq or per unit volume, and this is the rate of reactions Ra, we can express mole per unit volume per unit time. So, these are the things you should know, means these are the things or notations is and unit of that particular symbol. So, we should know and that are very useful for our rest of the study. Okay. So, it is usually volumetric flow rate, small v usually use or small v 0 also, okay, centimeter cube per second. So, that way volumetric flow rate. So, these are the things would be useful. So, with that also one more thing, so that we need to know, already you have studied. So, if you consider this is our general reactions A plus B going to C plus D. So, when a reactions we have started, we have taken the reactant component A and B that we are giving C plus D, that may be whatever the reactions, when reactions will take place inside of a reactor, we are getting the product from the outlet. So, once we get the product from the outlet of the reactor, so we have find out the concentrations of component C and D, these are the desired product. With that unreacted reactant, reactant B also will leave from the reactor. So, here how much percentage conversion means reactant A converted into C, that we can means measure or we can calculate. For that we have to use conversions, that is the number of moles of the reactant. If we calculate based on component A, then moles A reacted per moles of A charged. Okay. So, this way you can express Ca naught minus Ca by Ca naught minus Ca, that is the amount, means that is the difference of concentration initial and final. That amount would be the reactant materials A, that is reacted during reactions within that specified time inside of the reactor. So, by that way you can get the conversions, and next is the selectivity. So, that also we will get, means if here component C and D are the products formation is there. So, if you are able to calculate concentration of C in terms of moles. So, once we know means the component C forms in terms of moles, then we can know that moles of the C produced per moles of A reacted, means component C concentration of the C, that moles produced during reaction, and the amount of the moles of A that is charged or that is take part in the reactions, that if you know, then the selectivity of that particular component we can find out, and similarly yield of that particular component also we can find out. The moles, if you know that particular desired component or component C form, and the amount of the moles of A that is fed inside of the reactors. So, then by that way we can find out or we can calculate the yield of that particular component, or else if you know the conversion and selectivity, directly we can multiply that and divided by hundreds, that way we can also find out the yield of that particular component, that may be either C, here we have expressed in terms of C. Similarly, if we want to know for component D what would be the selectivity yield, similarly also we can find out. Okay. So, these are the things would be useful whenever further or next steps we will study, there it would be very useful. So, therefore, I am just discussing it. So, whenever it is required, so we will recall it and then we can implement, we can use that particular point. Okay. So, here we can use in terms of concentration, or you can use in terms of molar flow rate also, or moles per unit times, or you can express in terms of moles. Okay. Thank you.